Okay, welcome to General Physics Paradoxes. These are some things that happen in the physical world that are strange, not well understood. They might not be easily understood even by professional physicists, people thinking about it for a while, but they've caught the attention and interest of people, so we'll be reviewing some of these, some of the more interesting ones. So this is Robert Nemiroff, this is Michigan Tech, this is Extraordinary Concepts in Physics. Oops, sorry about that. I hit a bad thing there. And these lectures are available on the web through Starship Asterisks, through iTunes, and it's called Physics X. So let's get to one that is famous. A lot of these are famous. Archimedes' paradox. Can a large, massive object, like a battleship, float in a tub with only a little water, say a spoonful? Could you float a battleship on a spoonful of water? Yes, that's cool. No. That's just a little bit of water, only if the water is seawater. So you can go out and climb mountains thinking about this by looking out far into the distance. But I will tell you that yes, you can do it. It doesn't really matter once you're past the water that is in contact with the ship. The key factor is a factor of average density. The average density of the floating object must be less than the average density of the water it displaces. That is Archimedes' paradox. Past that, so you can have your ship here, in here, and you can have a little bit of water here. And so this is your ship. So let's put a ship thing there so you can see it. So this is a cross-section looking at it. Here's your vessel that has the water here. Now what happens here, you could have had a bigger vessel here and then taken out this and had this filled with water, would have been the same. So you can float a battleship on a spoonful of water. You can do it. Okay, this is tougher. It's famous. It's called the Feynman sprinkler for the person who made it famous, not the person who thought it up, Richard Feynman. So lawn sprinkler sprays water and hence rotates. So why would that happen? So we're going to look down on the sprinkler, and it has, let's say, arms like this, and the water comes in the center and sprays out here, and sprays out here, and sprays out here, and sprays out here. So you turn the sprinkler on, oops, I got it. No, it has to go. Yeah, that's right. This one's wrong. So I can back that one out. Okay, having trouble. There we go. Comes out here, and the whole thing goes around in a circle. So look, maybe you've seen a lawn sprinkler like this. Doesn't have to be this exact design. It has to have the general principle of its design. Here's what you do. You take this lawn sprinkler, and when your parents aren't looking or your spouse isn't looking, you fill the bathtub with water and you put it in the bathtub. And instead of hooking it up to the faucet, you hook it up to the vacuum cleaner. So you really shouldn't tell your parents or spouse because it's going to suck water in. And then you're going to wonder what happens to the sprinkler. Is it now going to go backwards because it's sucking water in? Yes, when you do that, does the sprinkler spin in the opposite direction? Does it spin in the same direction? Does it not spin at all? Or this seems easy, but I just can't figure it out. Which one of those is it? The famous Feynman sprinkler. And the answer is it spins in the opposite direction than it did in the lawn. So the physics is relatively complex, much more so than the lawn sprinkler in the air. And you know what? It's really complex. So I don't really fully understand the whole thing myself, so I proudly admit there are things in physics. I don't go around and look at the entire world saying, I understand everything. Oh, more physics, I understand this. Oh, I understand that. I am not the master of the universe in terms of understanding everything. It's the things that I don't understand that interest me, and actually I don't understand most things. This particular case is something that even comes up in physics context, which has been studied, which I don't fully understand, even after trying to understand it. So I am not omnipotent. So here it is, reading the answers from online and Wikipedia, which I think you'll get if you click on the links. So in principle, I'm told when the sprinkler is turned on, it will accelerate toward the incoming water. When the water is turned off, it will accelerate in the opposite direction. In between, when the flow of water is steady and one assumes that the water is frictionless, no angular momentum will be transferred, so the sprinkler will coast around. In practice, however, if you were to do this in your own bathtub, you would find you would be disappointed because many sprinklers have high enough internal friction so you can just not rotate them motionlessly. Also, water has a sufficient amount of resistance so that you're not going to get a lot of stuff going on. The coasting phase in particular will not be will not be borne out. So this is a case of something that might look simple, but actually it's quite complex. Sometimes if you try to reverse a system, you get a system that's crazily complex and it's difficult to understand, even when you're told what the answer is. Here's the tea leaf paradox. So this you can do much less expensively. You can do this while with your family or your spouse or your parents or your kids. So when you stir a cup of tea with tea leaves, where do the tea leaves usually end up? Do they end up at the bottom, around the edges of the bottom? Do they end up at the bottom in the center of the bottom? Do they float to the top and be around the edges there, or are they at the top in the center? So this is actually, people have wondered about this for some time. This seems like a relatively innocent thing. This demonstrates to me that even simple things that happen in real life in seemingly irrelevant circumstances can have deep, interesting physics behind them and be important beyond what people might know. This was analyzed and finally solved by Albert Einstein after general relativity. This was in 1926. He solved this one. So when stirring, he found out, stirring rotation is usually slower at the bottom. This, because you usually don't put your spoon all the way to the bottom, your spoon's near the top. This creates a secondary flow as opposed to the normal stirring where fluid rises in the center and falls at the edges. Now tea leaves participate in this flow but are too heavy to become lifted at the flow at the bottom. So there's a flow like this. Therefore they stay at the bottom and they're in the center. So you can try this yourself. Show your friends, they might not be impressed. So what is impressive about this is that it's not only of interest for seemingly needless reasons when stirring tea. People wonder what causes erosions of riverbanks, and it's fundamentally the same process. Riverbanks around the edges, stuff that's in the water, the stuff ends up in the center of the riverbank. Might cause a ridge or something like that, the river. Why is that? Same physics. It's the tea leaf paradox. Thank Uncle Albert for that one. Okay, here's an optical illusion I threw in because I thought I wouldn't have enough time, but I think it's really cool. When I saw this, I was amazed. So here are squares, A and B. This one's labeled A here, this one's labeled B there. And the question is, are they the same color? Are they the same shade of gray? And this seems like an easy one. And so, drum roll please, the answer is, questions, no, square A is darker than square B, yes, they're the same color. And this is one of those cases where maybe is actually the right answer. No. So actually, they appear to me to be the same color. In fact, here they are connected, and if you look closely, it's the same color all throughout. If you were to color off everything else, you start to see they're exactly the same color. It's like the shadow paradox, it's the shadow illusion. So one way to see this also is by, I'm going to go back twice real quick and then forward twice. Oops. See it? They're almost on top of each other. I tried to line them up. Well, play with this at home and go back and forth between the slides. And you will see this actually was an astronomy picture of the day too, where you can click between slides and see the strange illusion. Okay, moving on to the moon illusion. This is a famous illusion. Many people claim the moon appears larger when it's near the horizon. That seems that way to me too. When you look, here's an image, again chosen from the astronomy picture of the day, where the moon seems to be huge. It rivals this Greek ruins and this small tree in size. It's called the moon illusion, and people think it's true, it's not true, and that people get confused as to whether the moon is the one that looks like an orange or the one that looks like the pizza. So the moon is the one that looks like pizza with pepperonis, and the sun looks like the orange, just in case you're trying to keep that straight. So here's a time-lapse exposure which shows that the moon is always the same. Now when it's near on the horizon, people debate why this is such a strong effect and why people insist so much that the moon near the horizon is angularly larger. It's not, but we are comparing it to big things. Let's see, factors discussed include that objects near the horizon appear behind other objects and hence appear further away, and when you know they're further away, you give them a larger size, and that objects appear near other objects of smaller angular size appear larger. So you're comparing it to objects that appear smaller, and you say, oh, it must be large compared to that. But this time-lapse image shows that they're the same. All right. So the freezing water paradox is a really cool one. True or false, under some circumstances, warm water will freeze faster than cold water. So is that true because some freezers, they just do this? Or is this false because the warm water must first cool to the temperature of the cold water before freezing? Therefore, it must take longer to freeze. Which is it? Is it true or false? Think about it for a bit. And the answer is some freezers just do this. So this is your physics major or physics geek killer. So if you know a physics geek, you can ask them this question and be sure to tell them of the possibility that the warm water has to cool to the temperature of the cool water before it freezes, because that will make them sure that that's not true, that cold water must freeze first. However, we live in a complex world, and some freezers really do this, and it's been analyzed. And here's why. First of all, if you put warm water in the freezer, some of it's going to evaporate. So the amount that has to freeze is actually smaller, and it might freeze faster. Next, here's a cool one. I didn't think about this one. Many times, at least this isn't so common in modern freezers, but in older freezers, if you put warm water on your freezer, you're going to be melting some of the frost underneath it. And the frost has a temperature of 32 degrees pretty much. Well, it could be a little bit colder, but then you get down to the actual freezer components that are under it that are colder. So if you put warm water in, you're going to be putting the water closer to the colder component quicker. And so it might freeze quicker. Isn't that cool? Why warm water could actually freeze more quickly than cool water. But a neat thing, one of the things I found the most interesting about the Mpemba effect, also called the freezing water paradox, is that the temperature pattern in the water may differ between the initially cold water and the warm water cooled to the cold water's initial temperature. So even if you were to take the warm water and cool it to the cool water and put it in the same place, the cold water may freeze from the top and insulate itself. Whereas the warm water has the cold freezer component touching it or being close to it near the bottom. So what happens is frozen water can actually act as an insulator. So you won't freeze the middle part of the water very quickly if you start with cool water. But if you start with warmer water, you might freeze from the bottom, and then the nucleation will freeze from the bottom up, and it might go more quickly. So this shows that something as simple as freezing water can get into second-level physics and end up with something that's counterintuitive. And that's why this is one of my coolest examples of physics paradoxes. And that will wrap it up for this section of paradoxes. And with that, I'll ask you to keep shorter and away from your cat. Until next time.